W0 for Professor W0 for the hard work of our meeting course. He actually sets out a lecture on the figure Roma theory and figure coding theory. Today, he will give a workshop lecture on the technical of each curvature and the local winding volume bounding below.
So first, I would like to thank the organizer for the invitation, and also thanks for the very warm hospitality, and really enjoy the workshop so far. Today I will talk about the subject, and I will explain the notion of local rewinding volume later. But let's just. So here is what I'm going to talk. Oh, here's the definition. You have a Riemannian manifold, fixed point, fixed radius. Then you have metric ball. And so what is the notion of a local rewinding volume of this ball? It is a volume of another ball. What is another same radius? Another ball is you look at the ball and look at the remaining universal carving of this ball, just locally, remaining universal the ball. You look at the reference point, the base point. Clearly, the local remaining universal carving is not complete, but at the center point, at the base point, it contains the ball. Which part is complete? So project down to the ball downstairs. You say that ball on the local remaining universal cover is the local rewinding volume. Why you call local rewinding volume? You can see if you have something like this, you take a point here, you take a ball here. Right. The ball is like cylinder, almost. What's the local remaining universal cover? Is something like this. Right. If you look at the whole remaining universal cover, this ball is still like this ball. But locally, this point to this point, you have a ball here. The volume of this called local rewinding volume, just like rolled over, expand, and the volume. Okay, so that's the notion. So this talk, basically it's different from many talks. It's a survey type talk. So a survey on study manifold of local rewinding volume, Ricci curvature and local rewinding volume bound below. Local rewinding volume bound below the manifold could be very collapsed, like the picture shows. So our primary interest in collapsed manifold. Okay, so let's first quickly review a Riemannian manifold exponential map. Then you can write down, take a normal coordinate, you can write down volume density. You have two variables, one is radial direction, one is spherical coordinate. And then you differentiate along radial direction, you get this formula, where R is the distance function from the center point. If you stay in the so-called colocus, then this function is smooth. You can do this. And you can even differentiate twice, right? This is a Bachner formula for this function, where we know this Ricci curvature. Okay. And if you assume Ricci bound below, right, where the constant, here the constant could be 0, could be 1, could be negative 1. So just a constant. Then you take, you use easily to derive this, right? The inequality. Okay. Now, first you solve equal to h. If you on space form, that bar means the distance function on space form. Then you solve that. You calculate that. You calculate the Laplacian. Then you can think of this distance function as this kind of semi-solution, right? Then You look this, right? You look this at the one point, they are the same, right? Near origin. The remaining metric is the, and any space form metric is almost the same. Then you integrate, you get the volume inequality. This bar means a ball, or forgot to put R here. Radius R in a simply connected same dimension space form, constant curvature H. What happens if the equal, everything is equal, you can find the hash here is all eigenvalues are the same. So you know it has constant curvature by solve the metric. But if the volume is a maximum, a constant curvature plus maximum, that's implies this. So that's just quickly. So Gromov did a little bit more. He differentiate this one as a function in R. Take derivative, right? He found that derivative as R goes increasing, it's non-increasing. It's non-increasing. And you have monotonicity, then another form is for any 2R, the centered ball, then you have this control. All right. Again, what happens if equal? If this inequality become equality, then the ball, larger radius, is isometric to the space form ball. So there are two, I may say that the right color, I just meant it's important. The blue is okay. Well, okay. So what are the important? Monotonicity and rigidity, right? So recall that we can actually see the classical result easily from this volume comparison. If Ricci is bigger than the Ricci unit sphere, then the classical Meyer's theorem says diameter cannot exceed the sphere. And the maximal diameter theorem, Xiaoyuan Zheng, right, show that if equal, then only one manifold satisfies this condition. That's unit sphere. So the tradition proof, right, original proof is not using anything like this, right? Because the year you cannot use that. But we can easily see the diameter bound from monotonicity. Imagine you take a 2-point P, Q, that's realized diameter of the manifold satisfied condition. If the bigger than pi is here. If bigger, your Q is here. You argue by contradiction, you say the diameter must less than equal to pi. If bigger equal to pi, then you look the volume ratio as R increasing. Then you hit pi, right? You know the bottom one, the denominator cannot increasing after passing pi. But if diameter bigger, you have volume contribute on the top. It's no longer monotone decreasing, it's increasing, right? It's contradiction, so cannot exceed pi. Now what about rigidity? Rigidity you can see also from this. By you write 1 as the volume and then you rewrite at the top as 2 balls. Again, realize P and Q realize diameter, which is pi. So you take a ball, which is R, you take a ball, which is pi minus R. This P is R, and the 2 ball can have intersection, obvious, but cannot have interior. Intersection do not have interior. If have interior, we will guess the distance is pi. It's shorter than pi. So you have 2 balls not intersect, then you get inequality, right? Then you use the monotonicity, you get that. You can think of this as you already know the diameter is pi, so this is a ball pi. OQ is the same, right? So you either can look this as a P or Q, so you get bigger than the space form. R. Right? The top add up is 1. So you get this one. It must be, all the inequality must be equality. Then you apply this rigidity in this. You get that. So that's basically it. Volume information is the key of the right information when you study manifold with Ricci bound below. The most important application, I think, is this comparison easily derive the almost right Gromov pre-compactness theorem, which says any sequence Ricci lower bound below, you can normalize lower bound, always contain a subsequence, right? Convert in Gromov-Hausdorff distance. If a bounded diameter, you don't take reference point. If no bounded diameter, you have to take reference point. Always convert in Gromov-Hausdorff sense. Okay. Now let's go further look at the so-called maximum volume rigidity. And we know that if Ricci bigger than Ricci of sphere, then diameter cannot exceed, volume cannot exceed, diameter cannot exceed diameter, and volume cannot exceed the volume. So you have this inequality. And also, if equal, right, you look this as a ball radius, fixed point radius pi, then must be isometric too, right? So just 1 point. And then there naturally, you ask, whenever you have a rigidity, you ask so-called almost rigidity. If the volume is almost equal to 1, right? It's always less than equal. Almost equal to 1 is bigger than 1 minus small constant. Then you ask, naturally, if the manifold still diffeomorphic to a unit sphere. Then there's a quantitative maximum volume rigidity. First, okay, so these people, Parman coding and Chigger coding. So the theorem says, if that answers the question, you have a constant depending on dimension. Whenever you have a small constant between this fixed constant, if the Ricci satisfies this condition, then the manifold diffeomorphic to a unit sphere. So diffeomorphic to unit sphere, it can be, conclusion can be this, right? So it has geometric information. It actually choose a diffeomorphism that almost preserve distance. This isometry means a distortion distance by error, controlled error, where this constant it go to 0 as epsilon go to 0. So that basically means you can derive maximum volume rigidity from quantitative version, because in that case epsilon is 0. So you can actually have isometry. So quantitative version is important because not only you know rigidity, you know the quantities when approaching to the quantity which gives rigidity, how geometry and topology behave on the manifold. So that's so how you get this? How you get this, right? So just very briefly, if you look at the Ricci bound below, Chigger coding has important discovery. Almost volume ball is almost metric ball. So what is almost volume ball? That means you fix the radius, your ball under the Ricci lower bound is almost maximum. It's almost maximum. If equal, it's maximum. Right? Equal maximum, you know that this ball is isometric to the standard ball. But almost this So it's called almost volume ball because this is a volume condition. Almost metric ball means they are hot stop close to the standard ball. This actually implies if you slightly reduce radius, they are diffeomorphic to standard ball. And geometrically, it's very close, isometrically very close. But in Grommer-Hausdorff, it contains no infinitesimal information. If you look at the point, you look at neighborhood, smaller than this constant, nothing you can say about it. There's no regularity. Grommer-Hausdorff is very big geometrically. So how you get this? If volume look like a ball, the Hausdorff geometry look like a ball, right? That's space-form ball. And that's, yes, we know that space-form is a special example of word product metric space. For word product metric space, you can think of this, right? You can think of AB cross N. You have word product metric. That's a metric tensor equal to. Then you calculate Ricci curvature of this metric. That's equal to double derivative f and Laplacian equal to and if you look at the volume, this we call annulus, right? It's not open, it's annulus. AB, if I denote by this, okay, this kind of annulus. And the volume of, you have determined function R, you have minus, let's see, A. Actually, if you look at this A minus epsilon, A plus epsilon. So you can include A. That's equal to the integral f n minus 1's power over f n minus 1. So you completely determine this word product metric by this equation. If you have this equation solved, you get word product metric. And then if you have this condition instead of equal, right? You have this equation, so you can choose the function, right? Space form. But if the volume is almost equal to this, then you solve the equation, right? You solve the equation. It almost means this is not word product, but you solve the equation. Use that function. You use that function to show that it satisfies cosine law, underlying annulus, almost satisfies in Grommer-Hausdorff sense, the error. Then you realize it is word product space. If you choose the right one, the constant, right, the standard 3 constant, corresponding to Euclidean space, corresponding to the sphere, and corresponding hyperbolic space, you get that answer. But the proof is very technical, very quite involved. All right, but idea is this. Once you have that, then you have so-called standard, so-called Raffenberg method. You have manifold. It says if you have compact manifold, right? You have Ricci bound here. These all assume Ricci bound below. Okay. Okay. Yeah, this has Ricci curvature. Then if another manifold same dimension close to the fixed one, how close depends on the fixed manifold geometry of fixed manifold. Then they are diffeomorphic, but diffeomorphic can choose by holder. It seems to be the best regularity we can hope. Okay, so that's right. If you take this rho is pi, you take rho is pi, so that means close to the unique sphere. It's a fixed manifold, right? Standard, so it's diffeomorphic. Okay. Another rigidity with Ricci bound below is a special case where Ricci is non-negative. It's called splitting theorem, right? It's if a manifold contains a line is a minimum geodesic 2 expand to infinity. So it's not compact manifold. You contain the line. then the manifold, the matrix structure is rigid. It has to be a product matrix. Okay, and after reviewing the previous, right, you have maximal volume rigidity, then you have quantitative maximal rigidity. You have splitting, that kind of rigidity. Then you ask, what about quantitative? Quantitative means you just slightly change the condition, right? You ask what conclusion, to what extent conclusion holds. So first, Ricci non-positive and non-negative become almost non-negative. A line, if you have a line, it's very long, right? But if I have a segment line, then you have 3 points, 2 in the point and some point in the middle. Where you allow the point here, that means you have almost a line. Almost a line can be measured. You have 3 points, so-called excess. The distance, this plus, right, this is the distance of this plus this, subtract this. If that's equal to 0, that's a line. It's not equal to it, but very small. It's almost on line. So you have a setup which can be viewed as a quantitative, right, setup. And also the line is very long, so you hope that this is L, this is L, this is L, I'm sorry. This is L. You hope that the place you observe the ball of fixed size are relatively small, depending on distance. So that means you can virtually see a line, right? If you see very small, then this looks like a line very long. So what you can say about this? Then you can find the product matrix space. The dimension is not n-1. The dimension can be even 1. Just a matrix, length matrix space. You have point in the product, such as the ball centered here is Gromov-Hotov close to this ball. Gromov-Hotov close to this ball. All right. So basically says this. So that's the quantitative version. That's quantitative version. Now this has many applications in the Riemannian geometry. For instance, if you consider Gromov-Hotov convergence sequence, curvature bound below, any point on the limit space, you take a sequence, you blow up the point, you get a tangent cone if limit exists. I'm sorry. Okay. Let's go a little bit far. So if the limit space contains a line, then you know. If tangent cone contains a line, it's a blow up, right? You get a limit because Ricci is still lower bounded. I mean, you can. Okay. Then if the limits contain line, then you get a splitting, the tangent cone splitting principle. Okay. And this is very important. If you know the tangent cone can split, you actually give information about the good point, the structure good point and bad point, the proportion of that. If you assume volume is non-collapsed in the Gromov sequence, you have a reference point. Unit ball has a uniform lower bound. We call non-collapsing. You take any point on the manifold, not necessarily base point, convergent to the limit. Then, using the idea of tools improving the splitting or quantitative splitting, you can extend to the volume convergence. So the Gromov-Hotov information, the volume pass to the limit. Okay. Now, after reviewing this, here is our question. So maximum volume rigidity with Ricci lower bound. We know the lower bound is 1, or n-1. We have answer. But what about 0? Whether Ricci is bigger than 0, or Ricci is bigger than, here I mean h equal to 0, h equal to -1. Right? Seems no such result in literature. So our question is why? It's easy because you take a Riemannian manifold, you're scaling the matrix by square. The Ricci behave like this. If the Ricci, the lower bound is 0, then the lower bound preserved. However, the volume increased. If the lower bound is negative, it's also preserved. The lower bound become less negative. So that base means you cannot have no single compact manifold achieve maximum volume if the lower bound is not positive. Okay, actually, then what happens? You try to prevent scaling, right? Prevent scaling if you fix some conditions, say diameter. Even with bounded diameter, and it's not possible. The maximum volume achieved by singular space. So that's not possible. Now, seems the answer already have, right? But we didn't give up. Let's just start like 4 or 5 years ago. So we introduced this notion to overcome this problem. So-called local rewinding volume, local rewinding ball, and local rewinding volume, right? We already have this at the very beginning. And right, we use the notation tilde to denote the local rewinding volume. Rewinding volume. Okay. Okay. Obvious. If the ball itself simply connected, then the ball is the same, so the volume is the same. If otherwise, if the ball is not locally simply connected, then you have a strictly inequality. I once make a comment is local rewinding volume is not equal to global rewinding volume, right? You can take the manifold, take a universal cover, take a ball on the manifold, look at the inverse image remaining universal cover. But that ball could be still collapsed on remaining universal cover. For instance, the Ricci sphere. Ricci sphere simply connected, collapsed, right? The volume at any point on the universal cover is very small, go to 0. If right, but it satisfies local rewinding volume, lower bound below, lower bound. Actually, you can show it's not too difficult from the trigger Gromov-Foucault, the theory on collapsing. Any n manifold, if the section curvature bounded in absolute value by 1, then any point you can have a fixed radius depending on dimension. Which radius, the rewinding volume has a uniform lower bound. So that indicates that in study collapsing with Ricci curvature bound below, right? The good condition is you looked rewinding volume. If rewinding volume has no lower bound, then it's very difficult. It's just like very difficult to study. So maximal local rewinding volume. Once we introduce notion, we can simply reformulate the maximal volume rigidity to the following, which include all cases, right? So you have manifold complete. You take assume you have a fixed number, right? Assume each point on the manifold rewinding volume is a maximum. Then the universal cover has constant curvature. So the manifold, every point, the manifold is isometric to space form. And in particular, for h equal to 1, maximal local rewinding volume rigidity implies maximal volume rigidity. Simply you take a rho to be bigger than pi. You conclude this. Secondly, for any rho, right? Why you have to fix rho? For any rho, h fixed. I'm sorry. Okay, OH space satisfy this condition. OH space, right? Either positive, negative 0. Finally, why you fix the rho, right? The fixed rho, the reason is if you give any rho, why don't you look down on the manifold, right? On the manifold itself, then you can always, given any rho, no matter how small, you can always find spherical space form containing a point that the volume is strictly lies to this standard ball. So you cannot have the condition on manifold itself, had to be rewinding. But special case, exceptional is even dimension than positive, because you have injectivity readers estimate. Okay. Now, after this, it's natural, become natural to ask the question, what about quantitative maximal local rewinding volume rigidity, right? Given this constant, if I can find just find a constant such that whenever we have this, whenever the manifold satisfy almost rewinding volume, almost maximum every point, can I conclude that the same conclusion? But the model space no longer unique, just has basically it's a diffuse it mismatch constant curvature. We just say this because these conditions apply to all space form. There are infinitely many in each dimension. Okay. All right. So answer is no. Here, obvious counterexample. If you look at sphere, very large readers, curvatures near zero, right? Constant curvature near zero. And near zero, if you fix the readers, right, R large, this condition is satisfied every point, even on the manifold, right? But it's not flat. Does not meet symmetric constant curvature, zero curvature. And another thing is, this diameter go to infinity, right? And actually, in the negative case, this case is positive. Oh, yeah, positive. The negative case, actually, there are example by grammar of Thurston. They construct a sequence of a compact manifold dimension for each dimension bigger than 4. Section curvature can be arbitrarily pinched, but none of them admits hyperbolic metric. If section curvature arbitrarily pinched, right, this condition is satisfied for any small fixed number. But none of them for the right, none of this admits hyperbolic metric. Obvious diameter go to the other example, diameter had to go to infinity. So that means to have this quantitative version, additional condition is required, right? So so here we put a conjecture, means we put up diameter. Then and this should true. The quantitative version should true. To the and with a little bit of work, you can see that conjecture 1 implies that universal is not collapsed because, right? Because it's close in global hot distance close to a metric constant curvature. Constant curvature manifold universal is not collapsed. So by the volume convergence of coding, so you can see the universal original metric is now collapsed. So this conjecture means universal is not collapsed. Means you can actually, given this number, you can show that for any reference point, the volume has a lower bound. And that's the conjecture. Actually, conjecture 1 implies I already explained. Now we talk about some result. First, we show that conjecture 2 implies conjecture 1. If the universal is now collapsed, then all this condition implies conjecture 1. With additional conjecture, universal is now collapsed. What about conjecture 2? We show that if Ricci curvature has upper bound, not just lower bound, all these conditions plus Ricci curvature, the conjecture 2 holds. So that's now I state this. Seems the screen freeze. I cannot use the screen fix. I do not move the screen. Oh, move. Okay. Let's see. Okay, yeah, now move. So now like to the proof of argument quite different depending on the constant h. Positive, the positive 0 and negative 1 because the space form geometry quite different, so argument involve quite different tools. There are some common tools. That's the Cheeger coding theory I explained earlier. Geometric part. So that basically says you have a given dimension, rho and V. V means universal is not collapsed. In positive case, you can just say universal itself has lower bound volume. If local rewinding volume almost maximal everywhere, then you can conclude that it's a space form, diffeomorphic, but geometrically look like. Okay, this in the case, in the one case, if you take a rho can be anything here, just fixed positive. Rho bigger than pi, you get the previous the quantitative maximum volume rigidity. If rho bigger than, if you fix the size fundamental group, then if rho bigger than that, actually there are generalization by Abi of this theorem to this situation. But that situation also is non-collapsed because gamma fixed size. If in the theorem we put an additional assumption, fundamental group is trivial, of course the conclusion says you have a Gromov-Hausdorff right distance from simply connected manifold to this, right? Because they diffuse, so they simply connect to sphere. So you conclude the volume bigger than almost maximum, right? From this condition, plus simply connected, it's not, you cannot see this, why the volume become maximum almost. So have to through the proof. So that's quite different. And this theorem apply to all collapsed spherical manifold. Most all spherical space form, most are collapsed. So that's now what about negative? Negative because it's basically same because negative universal may not be compact, so you just put on reference point. The same conclusion true. But I want to point it out that positive negative has different geometry because negative, you know that any compact hyperbolic manifold at least has one point, the injective radius has lower bound. So the volume has a lower bound. It's not collapsed, even without bounded diameter in this case. In this case, the volume almost equal to with the diameter bound, so the volume converted. So in the negative hyperbolic case, it's actually volume is not collapsed, but we don't know a priori. We don't have the assumption. So we prove from the end of the result, we see this, but not during the proof, we always pretend it's collapsed. Now, this theorem has application, can be used to prove so-called quantitative maximum volume entropy rigidity. So first recall the definition of volume entropy. It's just measure the exponential growth rate of volume balls on the remaining universal covering as R go to infinity. A priori, without any condition, the limit may not exist, but actually it is. It's now trivial proof by many. Study the equivalent, the growth of fundamental group, length metric. Okay, now here is maximum volume entropy rigidity. It says, right, compact manifold Ricci bound below, the volume bound above by hyperbolic volume. So hyperbolic volume entropy is n-1. So the volume entropy cannot exceed n-1. In general, just less than equal. If reach maximum, if it's n-1, like at infinity, the volume goes like hyperbolic space, then it's rigid. Manifold itself is hyperbolic compact. And this work based on early work, Peter Lee and Jiaping Wang. Okay, now if you have rigidity, we ask if a quantitative, actually the question was asked in their paper, if a quantitative is true, we have an answer, yes, it's true. Of course, you have to have bound diameter. The question itself also asks a base bounded diameter, otherwise it's not true by the Gromov certain example. So if the volume entropy is almost how close to the maximum, depending on how close geometrically look like the hyperbolic space. I would say the Entropy 1 and Quartz, they have some partial result. Consider basically section curvatures negative case, bounded. They have the same conclusion. Okay. Now what about 0? 0 is different. 0 is strong. We call strong maximum local rewinding volume rigidity. So you have the same condition. Bounded diameter, you can normalize diameter equal to 1. Universal now collapse. Local rewinding volume almost maximum. Actually, you come up with, it's not diffeomorphic to flat manifold. Actually, isometric to flat manifold. Because it's strong, stronger. Because our condition is not equal, right? This is not equal. Why? Because you have a splitting theorem. Splitting theorem says if Ricci is non-negative, if the manifold diffeomorphic to flat manifold, it is isometric to flat manifold. So that's the conclusion. Of course, we can. This become rigidity. Then we can say what happens if we have almost rigidity, right? Quantitative. So we can change the lower bound to almost non-negative. You get really quantitative version, diffeomorphic, not isometric. All right, I see. So I just realized I talked too slow, and maybe I escaped the proof. But I would say, okay, maybe I say this. Yeah, the proof just for this case, right? I said then you have a background example in mind. If you have a sphere quotient length space where the fundamental group get larger, right? Then you have a collapse. It satisfies all the conditions, this space form. Now, instead looking this, you have the universal is not collapse, right? So that gives you a hand. You look the downstairs conversion, you instead look upstairs, but equivalently. Then you study upstairs convergence. You use the local maximum rewinding volume, which you can show that the limit is use trigger coding theory. You can show this is a standard sphere. However, limit group in this case no longer discrete, become continuous. Then you have to show that you can embed the fundamental group into the limit group using the convergence sequence. Then finally, you want to construct a conjugate map. So you get a contradiction, right? You say this actually equivalently diffeomorphic to this conjugate, then you get a contradiction. Just because the third part involves Ricci flow, I quickly see what ingredient involved. Ricci flow, you have maximum time. We use Ricci flow to improve regularity. But regularity, Ricci flow is not original metric. Information class for original metric. Ricci flow is nearby metric. So when you do Ricci flow, you hope that first you get regularity, then you get closeness, certainly. Then you can apply classical Riemannian, let's see, standard Riemannian tools, like center mass, to do this. Then we need the uniform time pseudo-locality. Here we interpret the pseudo-locality condition not as parametric inequality, instead Gromov-Hausdorff close to a Euclidean ball. Okay, and then also use most recent work, Bambler, Wilkin. It says if you look the Ricci flow in the time scale square tree, then the distance you can control. Again, but the distance smaller than that, nothing you can say, really. But we need regularity, right? So we need to get this result, which basically says if the manifold satisfies locally as a parametric inequality condition, right? You can have a definite flow time. When you flow time, the metric float and before can be controlled in the tensor, in the C0 distance can be controlled. The tensor can be controlled. If you rescale this, the actually tensor C0 norm can be controlled. It's not linear, but it's uniformly controlled. Yeah, so that's a play role, yes. Delta means here I state slightly more general. Instead of you look at two metrics, right? This metric is very nice. That metric is just a lower bound and satisfy this. Yeah, then you flow this a little bit. You can control that. This tensor in the scale, rescaling the metric, you have sigma alpha control. This combined with trigger Gromov sigma alpha convergence. But you know C0 norm is independent of scaling. So at least you get C0 norm common. And that kind of regularity we need. Okay. Okay. Now, so before we study the case where we looked at rigidity, right? A local rewinding volume rigidity. But what about the local ball is not maximum rewinding volume. It has lower bound. Actually, that information can be used to understand the limit space, collapsing Ricci limit space have allowed. Let me just state this, right? You have this trigger coding theory says this. You can define so-called regular singular compensation, right? The regular point means the tangent cone blow up is Euclidean space, unique and Euclidean space, a different dimension maybe. Otherwise, it's called singular point. However, the question is, what about the size, regular point, singular point, right? If the singular point too many, then in the non-collapsing case, basically, it's not say much. It's not say much. Have some piece information, but in terms of Hausdorff measure, which is related to distance, not say much. It's instead of renormalized volume, then you can say a regular point has full measure. Okay, but that's not cannot used to study the if you look at the distance in terms of okay. Then limit group, isometry group, and Y it's a Lie group. Y is no small subgroup, right? So what do you mean no small subgroup? If you have sequence group which look like very small, in a sense, each point the orbit is very small in terms of the days on the ball, right? You have sequence, these go to 0, then up to some point, this group has to be trivial, so-called no small subgroup. Okay, and let me maybe then borrowing no collapsing, all tangent cone has same dimension metric cone and singularity. By the splitting, you can see, you can work on that, you get this. Okay. If Ricci bound both sides, actually you can get the codimension 4. All right. So I didn't calculate my time, correct? Let me just say this. If universal not collapse, let's consider special case. The downstairs collapse, universal not collapse, then the information saved a lot. First, fundamental group information basically preserved. In that sense, if you have subgroup, its limit become identity, then the subgroup has to be identity. So if universal is not collapsed, but the fundamental group information reserved, then you can study downstairs collapsing. You can by using non-collapsing on upstairs and equivalent information, you can actually get a lot of this. Let me just say this. This is a quantitative version. This is a quantitative version of no small subgroup. With that, let me just put one slide. Okay, this one. So here I just want stop here. I take 2 more minutes, sorry. So you have, this means this is a collapse limiting space. But universal is not collapse. Universal limit, this x tilde means universal is dimension n. It's not universal x, it's just, let's say, the sequence remaining universal covering convergence to x tilde. If we assume has no small almost subgroup at one point, we can prove no small subgroup above. But so far our result cannot apply to just one point. We wish to do this. So we put assumption. If we are able to do this, then you know that collapsing downstairs, the limit space has integer dimension, which is now known without any additional condition. No contour example. Secondly, every tangent cone is a k-dimensional metric cone. It's like no collapsing case. Thirdly, in the Gromov Hausdorff measure, this regular point has 4 measures. So that's give in this case, right? Universal is not collapse. At least you can have a lot of. Okay, so I'll stop here. Sorry for take extra time.
Could you go back to the slide where you used the Ricci flow procedure of that?
Sure. Oh, here, I guess here, right? You mean this? This is a background. So this part just the only condition is this is not as a permanent. This part is a permanent pseudo-locality. This one is written in a note, their workshop last year, May something. From the note, they have this result. They gave a sketch proof, but we gave a different proof. But so we can use this. Yeah. It says, if you have Ricci flow, right? If the 2-point distance scale, then this one, square root t, then you can actually, the distance difference can be controlled very small. But smaller than that, let's say nothing, basically. Yeah. Initial data, all it has satisfied this local pseudo-locality. Local pseudo-locality condition.
In your proof of the tangent cone split, you need a 9, right? You need to assume a 9 in there. You put tangent cone split, if the tangent cone split,
yes.
You have 9 in the tangent cone split, and what?
No collapsing, need no collapsing.
And what one is the case?
Basically, it says you have volume, right? You know the volume. So the thing is, if you look at the manifold, Ricci bound below, right? So I think the core point is fixed radius, no matter how small, but fixed. That's not dependent on dimension. That's not depending on the manifold. If fixable, if you can say something about structure, geometric structure, topological structure of the ball, then you can literally say a lot of things about the manifold, topology, geometry, globally. For instance, like a section curvature on both sides, then you know that you can have a definite size depending on dimension. Such a ball, this fixed size ball, is either has only finite many diffeomorphic type, or it contains like between half-side ball and the ball contain a side, which is a normal bundle of infranull manifold, a disk bundle. for new manifold. Topologically, it's very collapse control. So in the section curvature bound below case, only non-collapsing by Paraman stability result, you know the local structure is like a tangent cone. If you homomorphic.
They use a tangent split.
No, they have stronger section curvature bound below, so they have top knockoff.
And when do you know the tangent cone have a 9? At 10 and 9.
Oh, okay. Yeah, there are many cases. So if you have limit space X, you fix a point. If the point happen to be in the middle point, some geodesic, or you have geodesic, any point here in limit space. If you have a geodesic here, any point here, split. Because the geodesic in the middle point, you will blow up, the geodesic become a line.
Oh, okay. In the original space.
In the limit space. Only if you're kind of near a singular point. Not so singular point. Anything you don't have, this point is not in any geodesic interior point. Only become in the point geodesic. It look like it's like a cone point or something.
If you have geodesic, if located in the interior of geodesic.
Right. Then it must split. Yeah.
Okay, then the sense first long.